Hello everyone. So we are continuing interval scheduling this part. Last part, we talked about the problem definition, and this part we'll talk about the greedy algorithm for the unweighted case. Let us go over quickly in this cardinality problem, a cardinality case of interval scheduling. We are given n jobs, 1 to n. Each job I has a starting time Si and finishing time Fi. In this example, the starting time is 0 and 10 for this job. So S1 was 0 and F1 was 10. And our goal is to find maximum number of maximum size subset of jobs where no two of them overlap in time. And we saw some examples. And then we propose this greedy algorithm that accepts the request that finishes fast. And in this part, we'll continue with the algorithm and we'll see why it works. So the algorithm is a scanning algorithm. We'll start from the left and go to the right, and we'll always accept the request that finishes first, and then we'll remove all the requests that are conflicting with that request. So in the beginning, we have R to denote the set of all requests, and T is empty, and we'll continue, and R will decrease, and at the end R will become empty, and T will contain all the set of accepted requests. So initially R equal to all requests, T equal to empty, and we sort requests according to finishing time. Now in the loop, we have this while loop. While R is not empty, we're choosing the I, which is earliest finishing time. And then we are adding this request to T, and we delete all requests from R that are not compatible with I, and we return the set of jobs at the end, return T when R is empty. Now let's run this algorithm on the example instance that we talked about. So in the beginning, we have R equal to all n 9 jobs and T is empty. And we sort the jobs according to their finishing time. So B, D, C is the order because B has finishing time 1. So B has first finishing B, and then D, then C, then E. This is the order we are getting. So F contains this array of finishing time, and the corresponding values for starting time is S. So 1 was finishing time, and the starting time for B was 0. This is corresponding. 6 was finishing time of E, and starting time is 4. Now, if we look at the algorithm, how it works. In the beginning, among all jobs, we find B has minimum finishing time, so earliest finishing time, so we'll select B. And then we remove all the jobs which are conflicting with B. In this case, in this time interval, A and D both are overlapping, so we'll remove A and D. In the intersection graph notation, where we create a node for each of the intervals, and we create an edge between two nodes if the corresponding intervals overlap. In this case, if you see, for B, we are selecting the node B, then we are removing all the other nodes which have edges with B. So A and D are removed. Then we have R has only C, E, F, G, H, I. Among them, C is the first one, so we select C. And then again, C has overlap with E. Other jobs are removed already. So among all the jobs which are present in R, it has overlap with E. So I'll remove E, and I'll be left with F, G, H, I. Then among F, G, H, I, F is having the earliest finishing time. So we'll select F and remove G, which has overlap with it, and continue. And finally, we'll come to the array when we have only H and I, and among them H is earliest. So I select H and I remove I, and R becomes empty. So we stop. At that time, T has B, C, F, H, and that is the optimal solution. So we are claiming that to be optimal solution. This is a solution written by the algorithm, but we'll prove this is optimal. So optimal here is size 4. We'll prove it. Now, what is the time complexity? In this algorithm, we do a sorting, which is n log n time. We sort the intervals according to the finishing time and level them in this order. And then in additional order n time, we can also create this array S if it's required. Now, we have to take care of the conflicts in the while loop. So the loop, if you look at this loop, it runs for, let's say, order n number of times. There are n jobs. Each time one job is being removed. So the iteration can run for order n times. And each job can have overlap with even order n number of jobs. So in the worst case, it can still become order n square. But now we see we can implement slightly carefully, and we can get an order n time algorithm. For that, we create this array S, as we mentioned. And now the approach is, if the selected interval k finishes at finishing time fk, Then we continue over the subsequent intervals till Sj, the starting time of the job, becomes more than Fk. So it starts after the finishing time. So we can think of this way, that we have F, and if first element has value 1. So in the starting time, we'll continue till we have a starting time Sj, which is more than 1, 2. And then we'll take the corresponding entry in F. So we'll skip 3 and we'll go to 5 directly. So in the next step, we take 5, but in this case, 5 has value 5. So corresponding entry will continue till we get some starting time more than 5. And then again, corresponding item will be F. So note that slight difference with the previous case where I claim that when we take this first one, then actually we deleted D and A both. Both are overlapping with C, with B. But now we are not deleting A at this point of time. It will be deleted later. So for example, here it's continuing, and then finally I got 9 here, and then this pointer will move till we get some starting time more than 13. So here A will be removed. So we are still removing A, but in a later iteration. Only thing is, in this way, the scan or the pass is only moving from left to right one time in the array, which is order in time. So total it will take order in time. Now, second point is why it is correct. For greedy algorithms, we saw for spanning tree when you talked about is a general template we are following. Same template we'll follow, and again we'll review at the end. So first, we'll try to show that, okay, if the greedy algorithm is not optimal, there's a contradiction, there is some other optimal algorithm. We can see the first point where greedy and optimal algorithm differs, and then we can construct another solution which is closer to greedy and is better than the optimal solution. That's a rough idea. Now, let's say A is a solution written by our algorithm, the greedy algorithm, A1, A2, AK1. So the K1 number of intervals. And we can sort them according to their finishing time. We can also sort them according to their starting time because all these are disjoint intervals. So there is an order. And then let's say we take the optimal solution, which you don't know, but assume that we know optimal solution. And this is a proof of correctness. So it's not an algorithmic proof. For this, just we can assume existence and argue on that, which is very important here. So we have K2 jobs in the optimal solution, and K2 is more than K1 because we are assuming greedy is not optimal. So jobs could be H1, H2 up to HK2. Here also we have sorted according to their finishing time. Now, if there are multiple optimal solutions, we take the one which has the longest prefix common with greedy. By longest prefix, I mean, let's say the first I jobs, if they're same in both A and H, we call they have prefix I common. So among all jobs, they have some prefix which are common, maybe it's empty. But if there are multiple solutions, optimal solution, we take the one which has longest prefix. Now we want to show that greedy makes same choices as the optimal solution, and for contradiction, as I assume that if greedy is not the optimal solution, A is not equal to H, and we know K2 is more than K1. Let's look at the first point where greedy works differently compared to the optimal solution. So let's say this one has I minus 1 prefixes are common, so A1 equal to H1, AI minus 1 equal to I minus 1, and this is the first point where they differ. It could be the case that I equal to 1, the first job is different, but that's fine. We just look at this point. Now we create another solution H prime, which is either more than H or it is the cardinality is same, but it has a longer common prefix. So one point is if I is less than K1, then we can just add later intervals to the solution, and L will have more intervals. Now, if we look at H prime, this H prime is the way we consider H prime is we take H as it is, except we remove HI and we add AI. And we want to show this is still a feasible solution. And if we show this is a feasible solution and with the same value, because it has same cardinality, we're just removing one and adding one same cardinality, then this has longer prefix common and we'll arrive at a contradiction. Because we assume that H has longest prefix common with alg, not H prime, if both H and H prime are optimal. Now notice the first fact that AI, it starts after AI minus 1 or HI minus 1. Because it's a valid solution, there is no overlap with the previous job. Similarly, AI ends before HI. The reason being we are using the greedy rule and we are always trying the job which finishes earliest. So finishing time of AI is surely less than HI. So first property is just using the feasibility of the solution. Second is using the greedy rule. So then fact 1 and fact 2 says that AI will not overlap with HI plus 1 and it will not overlap with HI minus 1. So H prime is a legal schedule and it schedules as many jobs as H. But it has a longer prefix common with H, which is a contradiction. Now, a couple of things to ponder that here we did not know opt explicitly, but we used it properly. We use this property implicitly in the analysis, which is very important. And second one is this funny thing that in physics we have this arrow of time, and which says that all the equations in physics, it will work if time flows from past to future or future to present. Both ways it's fine. Similarly, in this algorithm, we are scanning from left to right and looking at the earliest finishing time. But if we scan from right to left and look at latest starting time, will it work? So just think whether it will work or not. And this is the general greedy template which we are using. We first assume there is an optimal solution which is different from greedy. Then we find the first difference between the two solutions. In this case, this AI not equal to HI at that point. And then you argue that there's an exchange argument. We can exchange the optimal choice for the greedy with the greedy choice without making the solution much worse, which we did. We created H prime from H. And this is a template which we'll use for many problems like knapsack or other problems. Now, I will not mention a lot about competitive programming, but if you go to this web page, CP algorithms, again, there are many very nice problems related to scheduling or interval scheduling on this in this websites or the book on competitive programming by Hali Metal. There are a lot of examples there. In fact, if you look at this watering grass problem, if you look and read the problem, then you'll find that it is actually, though it may not look like an interval scheduling problem, it is actually an interval scheduling problem. And this is a very rich area, scheduling. There are multiple textbooks. Pinedo has one textbook, Interval Scheduling is a Survey. These are more advanced stuff. Those of you who are really interested in research and want to know more about this topic, scheduling is a very important area. It's one of my areas of interest as well. There are multiple conferences which happen only on scheduling, like MapSP. There are journals on scheduling, Journal of Scheduling, and so on. So I'll not talk a lot about scheduling. I'll post some links maybe in the comment. But with this, we end the interval scheduling cardinality case. And the next part, we'll talk about the weighted interval scheduling, where the intervals also have some weights. Thank you.